Hello everyone, welcome to our webinar. I am Maziyar Panahi. I lead the team behind a Spark NLP library. I will be your guide today as we explore the fascinating world of vector databases and text embeddings. We have a lot to cover today. Let's get started. The agenda for this webinar is to learn why RAG is so important when it comes to large language models such as ChatGPT or Llama. We will have an overview of Spark NLP, why its accuracy, speed, and scale matter so much when it comes to RAG. We will have two hands-on. One is with AWS Glue and EMR. I will try to use the Spark NLP to transform PubMed articles into vectors. And later on, I will use Databricks into ingesting the data and those documents into Elasticsearch. Lastly, I will use LangChain with ChatGPT, GPT-4, and Llama-2 in showing you how the whole thing comes together. Now, the limitations of large language models. While LLMs possess a vast amount of knowledge, they are not databases. The knowledge is static, meaning they don't update in real time. This limitation makes them unreliable for new or recent data. Additionally, they can't access private or use case specific information, which is crucial for many applications and use cases. The problem with the reliability issue or so-called hallucination is that when you cannot say when the LLM is being confidently wrong. So what you read feels like it's right, but because there is no source or reference or a citation that you can trust, that becomes a problematic for the lot of applications when the credibility of the information is very crucial. Now, to overcome the limitations of LLMs, we turn to vector databases. These databases store documents indexed by their vector representations, allowing for efficient similarity searches. This capability is crucial for grounding the LLM, especially when using retrieval augmented generation techniques, as it ensures the information provided to the LLM is relevant and accurate. A typical architecture of retrieval augmented generation goes like this. A user or yourself trigger a query with the instruction. It goes to a retrieval function. It turns into vector. It goes to a vector database. It brings back a bunch of documents. If you have other data sources, you can add on to it. But at the end, you have a context that hopefully it's similar to what you really want to ask, and then you pass that context with your prompt into your LLM. Prompt is usually something similar to based on the provided information, please try to answer. If you don't know the information provided, if you cannot answer, just say I don't know, and so on. So you have room to play with the prompt and do a little bit of prompt engineering. But in general, the embedding model that you use is critical because the embedding is what captures the meaning of a text. Now, how do you ensure the embedding is correct for the text you are using? Now, I have a few techniques of mine. I love dimensionality reduction techniques like PCA, TSNE, UMAP, and so on. You could also use clustering algorithms like K-mean and so on. Now here it's an archive, the entire archive. I vectorized them by using E5 embedding model. The color are representing of the categories. So in archive, the categories are like math, finance, legal, and so on. So when I look into how they are being positioned in this space, I wouldn't be surprised seeing articles about math sitting next to the articles about econ, sitting next to articles about finance, right? You also have different, another approach to check the quality of the embedding is here is the PubMed and the colors representing the journals that they're being published in. You could extract entities from those articles. Let's say you have a sample query, it brings back a bunch of documents. You extract entities from those documents, and then you see how they are being connected to each other. If it's about treatment, it's about adverse events, and so on. So these are some of the ways you can check the quality of the embeddings. However, there is a big issue with the RAG architecture. Half of it, the first half, is purely NLP. The pre-processing, chunking the data, trying to make sense of those chunks being sentences, having overlap, and the most expensive part is calculating the embeddings. Right? Now, I understand we no longer call BERT, Tiberta, Roberta, and so on LLMs anymore because we are dealing with large language models that are beyond billions of parameters. But again, these models, the contextual embeddings like BERT, they still require a lot of computations. They are 10 times faster when you're using GPUs. If you're on a single machine and trying to transform millions of documents into vectors, it may take forever if it doesn't crash in the middle. Now, let's see how we can overcome these issues. Now, accuracy matters, the speed matters, and scale is very critical. Here is a quick overview of Spark NLP. Spark NLP is an open source NLP library. It was initially built on top of Apache Spark, more precisely a Spark ML extension. It was first released and open sourced in July 2017. Uh, it's a unified solution for all your NLP needs and problems. In the last 5 years, continuously, it has been voted the most widely used NLP library in industry enterprise. And you can see the way that it's being downloaded every year and every release. There is a direct correlation between what we release in this library and how people react. And as you can see, there is a huge peak when we released a Spark NLP 5 a few weeks ago. Officially, it supports three main programming languages. You have Python, obviously, you have also Scala and Java. The Apache license 2 is the license for open source. And you have a language, programming language R, being supported by the community. There's a great community behind it. If you're interested, you can use that. Now, how Spark NLP position itself among all the technology and the tech stack you would expect from all the cloud providers, managed services, notebooks, and everything. It's pretty much the same thing as a Spark. It has a huge and very wide ecosystem that you can easily start installing Spark NLP and get it running. We have a huge amount of transformers, architectures, and models in Spark NLP. We've been building it and importing them by using TensorFlow as a deep learning engine uh, throughout the last few years. And you can see you have your usual mask language or the token embeddings or text embeddings like BERT, Electra, Longformer, Excellent Roberta, and so on. You have your usual token classifiers, sequence classifiers being used for part of a speech, name entity recognition, for text classification, like semantic classification, and so on. In fact, if you check Spark NLP models, how we have over 18,000 free and always to be open source pipelines and models that you can use. They cover wide range of languages. And we believe that NLP is not just English, and that's why we try really hard to bring other languages and cover all aspects of NLP and NLU. Three things that we really care when it comes to Spark NLP is first, accuracy. We have to have the state of the art of everything that is being released. Speed, even if you're in a single machine, we have to be the fastest. And scalability. There has to be at least close to linear direction, a correlation when you add more machines into a Spark NLP cluster. You can see exactly doubling, tripling, and so on. Now, accuracy, speed, and scale when it comes to Spark NLP. Obviously, we support optimized hardware from the NVIDIA GPUs and Intel, and recently we added experimental support for Apple Silicon. In Spark NLP 5, however, we added support for yet another deep learning engine, Onyx Runtime. Spark NLP loves Onyx because we care about speed and scalability. Now imagine if you can triple the speed of the exact same model that you used to use in Spark NLP 4. It's the same BERT-based case that you were using. Now, today, if you install Spark NLP 5, that model would be incredibly fast. In fact, I will show you quickly a few benchmarks. Now, a Spark NLP is between 3 to 7 times faster on a single server compared to Hugging Face, even though they're both using the exact same model. In this specific benchmark, I used the HP Enterprise server. It comes with AMD processor. I only use 32 cores. It has 80 gig of memory. And we went against Hugging Face based on PyTorch because the PyTorch is the first class citizen when it comes to deep learning in Hugging Face. We couldn't compare it to TensorFlow. It's much slower in TensorFlow Hugging Face. So between 3 to 7 times on a single server. It has pretty much the same thing, 2 to 7 times faster on a single node cluster set up on Databricks. But one thing that is very important to note is that when you don't have so much memory, you will notice that when it comes to 100,000 documents and 1 million documents, Hugging Face couldn't finish and it has out of memory error. We tried really hard to make this work so we can have a nice benchmark, but it just doesn't work. It needs much more memory, and when it comes to JVM and this garbage collection, the memory management of Java is much more efficient compared to Python. And the scalability, we really want to have like a zero code change. You have the same exact code. You don't need to change anything when you go from one machine all the way to 16 machines here. You can see almost there is a linear correlation between how many machines you add and what would be the end result of the benchmark. Now, in Spark NLP 5, we also try to bring the recent top of the leaderboard of text embeddings, which is E5 and Instructor. We released them in Spark NLP 5. They all beat the text embedding order by OpenAI. And we thought it was very important for the community to have access to free and open source embeddings that could scale, and so they can do it over millions of data. But here's the thing: if you today, after 2 weeks that we released it, if you look today, the same leaderboard, you will not see E5 and Instructor on top anymore. There are different models. Still, the OpenAI embeddings are at the bottom, so that's a great thing. It's a win for open source community. However, it's just very continuously evolving, right? And we are not behind. If you go today to the Models Hub or Spark NLP, you will see those models. We quickly import them, and it's accessible to you when it comes to Spark NLP 5. Now, I would like to show you some of these things that I talked about, right? So let's just start with AWS Glue and AWS EMR. Now, so what I have here is Spark NLP code that I'm using for AWS Glue. This part is, I'm guessing if you're familiar with the Glue, this is just for Glue to just create the Glue context and start the Spark session. You no longer need it in EMR. But what you need to just focus on is that I'm just reading simply around 100,000 articles, full metadata articles from PubMed, and they don't have any vector. I will count them. I would like to show them to see the count. The full abstract is kind of like a concatenation of the abstract text because it's kind of like an array of text. I would like to connect them together to have a full text. And then it's a very simple pipeline. You have your document assembler, you have your text embedding, and that's it. That's pretty much it. And I will write it on this so I can reproduce it and load it anywhere else in any platform without being stuck in AWS, right? So that's the whole point. And pretty much I do the same thing with EMR, except in EMR, I have to have a jar so I can submit it. So here's what I'm going to do. I have Terraforms, and I already have them ready. So I need to put my MFA here. That's it. Need to log in, kind of. Secure AWS is a happy AWS. And I also have this code that I do, which would put everything on my environment. So I could actually use it when I'm launching my. So here's what's going to happen. I'm going to have Terraform in it. I'm just initialing Terraform, make sure everything updated, and then I'm going to apply. Hopefully, let's see, in a live webinar, we can do it. So it's just going to show me the plan. I'm going to say yes, but that's that. And I'm going to do the same thing here, apply. And that was quick. You see, it just added all the resources for Glue. And you will see in EMR is not the same. EMR is going to take a little bit of time to create everything. And I'll tell you why, right? So I'm just going to show you the glue that here we should be able to see a job coming. Well, I just can refresh here. Yeah, you can load the page. It's okay. And there it is. So our job is being created. And hopefully, if we go in, we can see the code. What happened in this glue Terraform, it took my local Scala code and it just puts it on S3 and it told Glue, go there and look at it. And you can see it here. That's exactly what you saw locally, which is great because I could change it locally and then run the script again and it will put it on S3 and I'll update it. What happened here in the run, I should see it running now, right? It's a start running, everything's perfect. And also EMR. Let's look at the EMR. Okay, we can reload you as well. Let's have a filter, 1 hour, apply, and there you go, a start, right? Now, I'm just going to quickly go back to the slide and show you something while these two are coming up, right? What's the difference between AWS Glue and AWS EMR? Now, AWS Glue is serverless. That's why it was so fast. The startup time is just incredibly fast. There is no such thing as provisioning or even demanding some instances. The resources are just available, already up and running. I think the boot time, everything to be up and running with a Spark is around a minute, but these are cloud, so it's never always the same time, depending on the, when in the during the day you are asking those, requesting those resources, the whole thing might change because it's a shared resources between everyone. Now, Glue is not flexible compared to AWS EMR, meaning that, as we just saw, I had to add a code, so it's not a jar. And the dependencies are not flexible. You cannot have a complicated code when it comes to Glue, but it is incredibly fast, right? It means that Glue is a managed service as well. You have to pay a little bit more because they're managing it for you, the scalability and everything. As opposed to EMR, it's a simple EC2, so you can even use spot instances if the time of the job doesn't really matter, so you can just wait when it's the cheapest to run that thing. Now, when do you use which, right? If the job that you have is not time sensitive, I would say go with EMR because you can use a spot instances. It's much cheaper. It's okay price wise. I think AWS EMR is the winning. If it's a complex application, you have a lot of dependencies, you need to package everything in one jar, in Uber jar, and then you have to be very flexible in the type of the machine you are using, the CPU, even the architecture. You will go with the EMR because it's easy to, you can choose everything, right? Now, Glue is like if it's more time sensitive jobs, right? Sorry. If it's more time sensitive jobs, you will go with the Glue because it's just super snappy, so quick. If you have to do something, let's say 3 times per hour, you cannot do EMR because every time it's going to take 10 minutes just to start and boot and come up, right? You go with the Glue if it's time sensitive and you are doing it all often. Also, if what you do is ad hoc, small batch jobs, if it's going to be like, it's not worth it to wait 7 minutes if the whole job is going to take 1 minute, I will also advise for you guys go with the AWS Glue. Now, if we go back to our own demo, you will see EMR is still starting, right? It's still not even in the bootstrapping, still in the starting kind of like a stage. Oh, now it's bootstrapping. Okay, I was wrong. Now it's bootstrapping as opposed to AWS Glue. We are in 3 minutes. I think we have some output logs. Let's go check the output logs because in our code, we should be able to see something, right? And that's the thing. All right, logs here. I'm going to close this thing to have more room. There is one log here. I'm going to open it. This one log here, we just did hello from Spark NLP, obviously. Welcome to text vectorization. Total number of article is around 100,000. I could probably zoom in. Okay, that's 100,000 articles. What's in those articles? This is like a full schema. These are large, right? This is not just a title and abstract. This is a huge amount of data coming from Midline FTP. So you have everything about author list, article title, journals, and so on. You got everything, even the mesh and all the chemical lists that they are here. Now, what else do we have? Okay, it's starting downloading E5. We're using E5 because in my test, E5 did great, to be really honest. But you could change anything else. You can go with E5 base version 2. Apparently, it's a bit more accurate. You can even use large if you like. You can use instructor Excel. It depends on you. I mean, we have so many embedding models that you can do, right? Okay, the EMR is also over. I'm hoping it's now in the running. Okay, it's running. When it's done, it will tell you it's terminated, right? So it took 5 minutes, 32 seconds to get up and start, and now it's actually doing the process. So what I expect from the glue is to be finished, and it is finished, succeeded. Took almost 5 minutes. It took almost 5 minutes to transform 100,000 PubMed articles by using E5 that just came out like a few weeks ago and save them on disk, all the information with the vector so we can use them later, ingesting them in the database. Now, couldn't we just have the whole thing together, like ingesting them at the same time? That's true, but I would like to demo multiple technologies so you know that, first of all, you're not stuck in one. You can just move around. Second of all, you get to know how to use a Spark NLP and what comes out of a Spark NLP in different managed services. Now, let's look at the EMR and see, okay, 6 minutes is still running. We don't have to wait for the EMR to be finished because I know how long it takes. It will take exactly 10 minutes. And if you remove these 4 minutes that took to come up, it's pretty much around 6 minutes. So it did pretty similar to glue. It's just that the starting is incredibly time consuming. That's like almost half of the whole process, right? So if what you do is time consuming and you have to do it like very often, you probably don't want to go with EMR. And this is pretty much the same thing for every managed service or any service that has provisioning and it doesn't have serverless, right? Even the database, when you're starting the cluster, it will take pretty much around 5 to 6 minutes to the whole thing to come up. All right, so it's still running. We could leave it on like that. We will come back to it later. All right, so what's next? Let's go to Databricks. Let's go ingest some data into our Elasticsearch cluster. All right, so I have Elasticsearch cluster, and one thing you have to notice about this Elasticsearch cluster is that, first of all, it's the latest version that came out, 8.9. It has the most optimized KNN for semantic similarity. Now, the reason I chose Elasticsearch, because as you can see, it's the cluster that I have that I've been using it for a long time. I think I've been using Elasticstack since version 1. It's been a long time, yeah. And you have around 7 billion documents on this a specific cluster, almost half a terabyte of JVM heap, 17 servers, and so on, right? So this is the cluster I have. But one thing you have to know about this cluster, this is not in AWS. This is in France, in Paris, on premise, right? Now we're trying to use Databricks in order to ingest something that probably launching machines in AWS in US region into something that is on-premise here. I thought it's a nice use case to do a little bit of a hybrid situation and see what it goes. Now, here in this notebook, I'm not going to run it. It's pretty much the same code we just ran in AWS Glue and EMR. Read the data we have in PubMed. These are the PubMed articles. It was a process before that. We synced the FTP, got the XML, read the XML, and then we save them here, right? This is the same schema that we had. Pretty much the same thing we did, like, concatenating everything into called full abstract, and then running the exact same pipeline, and then saving it on disk, right? So I already have the whole thing here, right? And all I need to do is just to load it. And as you can see, it's already loaded, right? I'm going to do it again. Probably going to take like 50 seconds to read the whole thing because it's massive. All right, I was wrong. It only took 3 seconds. It has around 21 million articles. And the vectors are already there as well, right? So if you look inside, you have the article title, you have the full abstract, this is your PubMed ID, and you have all the embeddings here. Perfect. So now what? What do we do? Now here is the where I connect to Elasticsearch. Again, the Elasticsearch is nowhere near Databricks or the servers of Databricks, right? It's here. What I'm using is the native Elasticsearch Spark connector. And these are the configs that I will connect to, right? Now, since they're not even the same continent, let alone on the same network, I have a reverse proxy by using Nginx. So I put the domain here. I'm using HTTPS for security, obviously. I have a username, password. It's also basic authentication as well. And then I have a bunch of other things that I could share with you after the webinar, but there's a great documentation about this on Elasticsearch docs that you can look into it. But what basically does is just going to connect to the cluster I showed you here, right? And then I'm just going to prepare it like if the embedding, I'm going to rename the embedding from embeddings to embedding because I like the name embedding. I would like to keep everything as embedding in Elasticsearch so I know when I'm doing semantic similarity. Pretty much the same as schema, so everything is fine, everything is perfect. And this is how it would look like. Now, this is how you will write it in Elasticsearch Spark. It's very simple. Again, I'll have a sample. I'm going to pick 2% out of those 21 million articles because it is a live webinar. And you just write it. You could update, you can upset. As you can see, you can have different strategies like go year by year and create a new index and then call it PubMed dash the year, like 2000, 2001. In fact, I was testing for performance and I've done it already. So I have PubMed 2000, 2001, 2002, all the way to 2023, right? That's one strategy of going, one shard and one index. And then I have one index that has everything. It's 12 shards, scale over 12 machines. It has 17 million because, I didn't put the 2023, right? So I try to see which one is faster, which one is better. When you're dealing with larger scale data sets and you could actually use technologies that they can scale, the testing and evaluation comes much, much easier because I could do this all day, right? Instead of waiting days or a week to do this, I can do it all day. But for the case of curiosity, I'm going to create a new index called PubMed Just Testing, and I will just try to ingest 2% of the data in here. Now, what's happening here is that in your Spark executors on Databricks, I have 10 workers. Every single of those workers going to get batches of articles and start ingesting them at the same time, right? So even ingesting is in parallel and distributed, which is great. Now it goes from Databricks, AWS in United States through my reverse proxy Nginx in France, and it goes to Elasticsearch cluster on-premise in Paris, right? Now this is, I'm guessing, start writing it now, right? You have 320 partitions divided between 10 workers. Each has 32 cores, perfectly divided. Nothing is idle, right? Think about it, like 10 workers, 32 cores, 320. So every single one of those cores must be running now. Now, if I go back to here, I don't have any index called PubMed Just Testing. I'm going to reload. Let's see. Oh, it's here. So I'm going to maybe sort it by the number of documents. Oh, already ingested 100,000. That's a lot, actually. All right, let's see. Here is still, maybe we could look into a Spark. No, maybe, I don't know how to show the Spark UI. Interesting. All right, it started showing some updates. Okay, perfect. Because I could see some documents going into Elasticsearch Index, but I couldn't see the update here. Must be the notebook not updating it, right? All right, so I've done this before. I think it takes around maybe 2 minutes. But again, these are all cloud instances. They are generic at best, and they are shared resources. So depending on the time of the day and how much people are using next to you, the quality of it could, be affected. Sometimes faster, sometimes it's slower. Now, while we're waiting for this, let's go see if the EMR is over. Let's see. All right, terminated. So it's perfectly finished. It's done job. It's 12 minutes. 4.5, almost 5 minutes of it was starting, bootstrapping, installing everything, right? So I would say it's a little bit slower than Glue, but in total, it took 12 minutes to vectorize and transform 100,000 documents from PubMed into E5 embeddings. All right. So this is done, 2 minutes, 46 seconds. Now, uh, I don't know exactly the exact number of documents that would be 2%. Let's do refresh and look at this thing here. Maybe I could just say PubMed just testing, and it's still refreshing. So when you refresh, it will make them available for search, right? So one of the good tips is that you make the refresh, you disable the refresh during the bulk import and ingestion, because you don't really need them, and then you will see them right there. Okay, so let's see. We have 290,000. Is that true? Is that 209,000? 2%? I mean, it's close to 300,000, right? That's a lot of documents. We just ingested, oh, wow, that's a lot of documents. Almost 500,000. Wow. That's a lot. Almost 500,000. That's a lot. I don't even know. Wow. Okay, that was really fast. That was really cool. Okay, so we did it. We on a live webinar, we transformed 100,000 of PubMed articles by using E5 that just came out like 2-3 weeks ago, top of the leaderboard, into vectors, and then we use Databricks to ingest them into some Elastic cluster on premise in Paris. Really a strange workflow. Well, now what? Okay, right? Now we're going to use them. Now we have to use these documents here. All right, let's go into my Qt documents and notebook. We will use, the first thing first, I would like to show you the zero shot. The zero shot means that everything you ask will come from the LLM knowledge, right? Whatever you use in zero shot is that you don't have any examples, you don't teach the LLM anything, you're just simply asking it, right? Translate this thing into, French, for instance. J'adore la programmation. Okay, that's true. You could have system message, you can have human message, obviously in LangChain, that's how it works. My favorite is having templates, so you don't have to keep repeating yourself. You can just put the input language, output language, right? It's pretty easy, and then it will work, right? And you have now German, you can keep changing it. Now, if you want to have a conversation with the history, you can add memory. You have many, many memories. If you, in fact, you could search by memory here and just do it like that. So you have many types of memories, right? Another favorite of mine is the buffer window, because you could say only keep the last three messages in the memory, because I mean, who would go all the way back and try to ask something? But it's up to you, right? So this is how you can do the memory and then ask questions. You're a nice chatbot having a conversation with a human, and obviously I just ask, how can I assist you today? My name is Maziyar, and tell me a secret about Darth Vader. Okay, well, one interesting secret is the iconic breathing. That's not really a secret, but okay, I get it. Do you still remember my name? If it says my name is Maziyar, it remembered. All right, of course, Maziyar, I remember your name. All right, perfect. So that's the memory. But problem number one with the zero shot is that, you remember, being updated. It's not. It does not know what LangChain is at all, because it just stopped learning at some point a year ago, 2 years ago, I don't know how long ago, but LangChain is new, so it doesn't know anything. And the second problem is that if you ask a serious question, like let's say, will consuming red meat or any animal-based diet has a higher risk of heart attacks, honestly, I don't trust the result, because I don't know. There are no reference. Like this is it says there is evidence to suggest that consuming excessive amount of red meat, particularly processed red meat, etc., etc. I have zero reference from this, so I don't trust it. Right. So what do we do? RAG, retrieval augmented generation. Vector databases are coming to help us. You have your question, it goes to your database, brings back a bunch of documents, you format it however you like, you add it with your prompt, you go to your LLM, and you get your answer. If you have a memory, then you manage between these two, and we'll see in the future, right? So, and this is how we did it before, right? We took the source, which was PubMed, we loaded, transformed it, we did the embedding, we stored it in Elasticsearch, and now we're going to use it, right? As we can see, let me run this too. Okay, perfect. As we can see, this is a local address, IP address, means that this notebook is hosted right next to the Elasticsearch, right? Perfect. I'm going to connect to that by using Elasticsearch Pi library. That's fine. The cluster is healthy. You can see the number of nodes are 70. And as you can see, there was like the index pattern, like PubMed dash something. That's nice. I want to use that. So from 2000 to 2003, you have around 21 million articles. Now keep in mind, these are all with the vectors, right? Because we just used Databricks. They were all with the vectors. We put them in. Perfect. So here I am using another library to vectorize somehow, transform the input, instruction, query, whatever you want to call it, into embeddings and then pass it to Elasticsearch. Why is that? It's really important for you to understand that you are not stuck when you are using a Spark NLP. Just because you have data engineers, you have a workflow, job flow, airflow, whatever it is, and you on a regular basis, daily basis, weekly, you get a lot of amount of data, you transform them into vector and you put them in your vector databases. Doesn't mean all the people after that has to use now Spark NLP. That's not true. If you can use it if you like, but you don't have to, because the model is the exact same model, right? It's E5 base. Nothing changed. We don't own the model. Hugging Face doesn't own the model. It comes from someone else. The weights are the same. The way we calculate it are the same. And this here would be an evidence of how you can use a Spark NLP to transform millions of data into your vector databases and then use Hugging Face or sentence transformers in order to query those data back, right? I'm going to load them now. Thankfully, I downloaded them already, so we don't have to wait to download them. This is a pretty normal and usual averaging pool, so pay no attention. This is just a simple, let's get something and just pull them together. Now, in Elasticsearch Pi, how you do your KNN, it's a very simple body. You have your query that goes into lexicon, and it probably reduces the amount of data that you want to query. Like, let's say if you care about the year after 2005, this is where you put it. And this is your typical KNN. The field was embedding, obviously. Query vector is the embedding that comes from the function that we just saw. How many? 10, number of candidates among 100, and then you have the boost, which goes between these two, which one should go first, and so on. Now let's have a method called Elasticsearch Similarity KNN Search. I'm going to write that. What it does is just going to go into my Elasticsearch, get the hits, come back, and then get the abstract, get the metadata that I need, and format them in a list of dictionary, right? Let me show you an example. This is how it looks like. Page content, that's content that it was actually vectorized. And then you have the metadata, which is the PMID, the year, article, title, and so on. Now, let's go to LangChain Retriever, right? So you have this thing in LangChain that it comes already with a lot of retrievers, and the community already provided a lot of retrievers. But I like to do my own thing because I like flexibility and control. So I simply converted this function that I have into my own retriever. It's actually called my own PubMed retriever. Right? What it does is just get relevant documents, call that a specific function, and format it in a way that LangChain likes it with a document, right? And the page content and metadata were already there. So this is perfect. Let's go do that. And let's use it so we can see how it looks like. Pretty much the same thing. It just has this document around so you can use them in different, chain of LangChain. Now I'm going to use GPT-4 now. The reason I don't like to use GPT-4 for RAG is that I think 3.5, especially with 16K context limit, is all perfect. If it's not too complicated, it's not chain of thoughts, you don't have very complex instructions, GPT 3.5 does a great job. And it's not that slow, right? GPT-4, it's a little bit slow. I mean, actually, it's a lot slow. Now, if you look into what happened right now, is that we had a prompt template saying only use the content inside the document section, and that's the document section, right? And we put whatever comes from the retriever inside here because these are like a template, right? The context and the question. And that's it. And we're asking GPT-4 to read it. We are printing here whatever comes from those documents so we can look into them and seeing what is the answer and why did it answer it like that. And then we wait for the GPT-4 to come back with the result. It's still running. If it was GPT 3.5, would have been immediate, but GPT-4 is a little bit slow. I think it's a lot slow, to be honest. And anytime now, okay. Maybe my fault. I should have turned on the stream, then it would have been easier to wait for the end. All right, so we're done. Okay, so that's a very nice answer coming with the bullet points, telling us why it thinks, based on the given information, why it thinks your heart-related diseases would increase if like if you're in a high temperature, like in general, how would the climate change affect our health, individual health. Now, GPT-4 is slow and it's also expensive. So thankfully, we have open source large language models, Llama-2. I have 13B and 17B already running by using TGI by Hugging Face. These are the ports. These are some of the instructions. Hopefully, I turned on the streaming so we can see that. Unlike GPT 3.5 or 4 or anything comes from OpenAI, you need these special tokens for Llama-2. So it means that I have to change the template when it comes to retrieval Q&A in order to make it work. Otherwise, Llama won't work. So I have to tell it, this is my instruction. The system will end here. That's a system prompt. Then here would be my history, context, and then the user instruction ends here, right? And I'll create two memory, one for my 13B, one for my 17B, so we can see them in different, after different runs. Okay, so let's go with the 13B Llama. I'm going to ask the exact same question. Hopefully this time is in the streaming so we don't have to just look into the empty screen. All right, so the answers are long, the answers are fun. I mean, I can see a lot of similarity with GPT-4, right? Keep in mind, you could improve what comes out of this by having a better system prompt and by having a better instruction. You could improve it a lot actually. But we didn't do that for GPT-4. To be fair, we won't do it for Llama as well. Now, 70, I noticed 70, it could handle much more complicated instructions, but sometimes when you ask question, it's a bit shorter. As you can see right now, comparing 13B to 70B, I'm pretty happy with 13B. Also, less GPU memory, also much faster. So you have like 100 tokens per second probably. All right, so if you look into the memory of the 13B and 70B, you should probably see what's going on here, right? Increased frequency of severity, etc., etc. So this is the only thing we had. If I ask another question, let's say from Llama 70B, list some of the existential threats of the U.S. energy grid, you will see that these are the answers. In the memory, I should see this last one as well, right? Okay, perfect. We can see that as well. All right, we did that. We made a retrieval Q&A by LangChain, right? And we used the Elasticsearch data we had, that we used Databricks to ingest it, and we used AWS Glue and EMR to transform them, right? That's perfect. I did all that in half a day, by the way. This 21 million, pretty much quickly. I screwed up a few times. I did it again because it was so fast. No harm done, right? But the problem is that every time you ask a question here, it's just going to go query it, right? Because it expects to be queried. Like you ask something, it goes to your database, it brings back documents, and it answers based on that. I'm not sure it could even use history, but even if it use history, I mean, right, it's not really like, it's a hit and miss kind of. And if you ask anything else, like let's say I'll ask it, my name is Maziyar, what's your name? I'm pretty sure the documents coming back, either nothing will come back or would be a bunch of junks coming back. So the answer would be good. Another thing I would like to show you, just for the fun of it, is agents. Like how do we take what we already have, make tools, like this is my PubMed, right? It's the exact same thing we already had here, the retrieval Q&A. I have some description when to use this tool. I want to add Wikipedia and calculator next to it, and we use agent. we're going to use agent to decide which one to use based on the question, right? So I have my chat history. I'm going to use chat conversational React description. I'm only going to do 3 max iteration. That would be fun. All right, that's started. Sorry, I have to run this first, then run it. So the agent question answering memory should be empty as it is now. All right, hi, what's your name? Probably it's gonna tell me final answer because I don't think it's any of those tools is appropriate for this. All right, okay. I'm an AI developer, OpenAI. Obviously, it's GPT-3. All right, nice to meet you. My name is Maziyar. And then it's still gonna go to the final answer and it comes back. All right, how can I assist you today? What is 13 raised to the 0.3432 power? I expected to be using calculator, and boom, it was using calculator. Oh, that's great. It is using calculator, and that's the final answer. The result of this would be this, and you have the output, right? Perfect. So the calculator worked. What about this one? Will consuming more red meat result in higher risk of heart attacks? I expect this to be used PubMed. And the fun thing is that it's going to use my Llama, right? You see, it's streaming. We mixed 2 LLMs right now, right? This part comes from Llama, and then it wants to answer, it will use OpenAI to answer the final thoughts. That's awesome. This comes from Llama 70. This whole thing, retrieval Q&A chain from PubMed, explaining everything perfectly coming here. If it's too expensive to go to OpenAI, you can do that with the open source LLM. For some reason, if you don't want to have the whole thing on one LLM. And once this is done, the observation is here. That was the answer. It's going to go to the thought, and the thought is the OpenAI. It's going to ask OpenAI, now give me the final answer. Does it increase or it doesn't increase? All right. So here's the whole output at the end. Research indicates that consuming more red meat can indeed increase the etc. etc. This is likely to do what? And here the important part is that, however, it's important to note that this is a complex issue, and other factors such as overall diet, lifestyle, etc., also can significantly, either improve your heart health or decrease it. Now, it didn't give that answer last time we asked the GPT-3, right? We asked that, hey, what do you think? It will like adamant to be saying, yeah, there is a direct relation between red meat and heart attacks and heart diseases. But here it's saying like, it's a complex matter because the input being given here, it was telling you a little bit like, all right, you know what, probably not that direct. Okay, I want to continue. Do you still remember my name, right? It's important for me. And I want to see this question should not go into PubMed or Wikipedia because I told them my name. Yeah, there you go. Your name is Mazia. Perfect. Now, who was the president of US in World War One? Sometimes it goes to Wikipedia, sometimes it goes to Zero Shot. Right now, it went to a Zero Shot. Why? Because it decided that I have this information. I mean, it's World War One, hasn't changed, right? If you ask something recent, it will know. I was like, all right, I don't have that information. But a World War One, I mean, it hasn't changed, right? It's not going to change. So it's going to answer you from the Zero Shot knowledge. Again, you can change the prompt and say never answer from your own knowledge, but why not, right? Now, if you do enter X enter, this is a very new thing from Wikipedia, right? This is Wikipedia. Expect it to come from Wikipedia. Oh, thank you. Perfect. All right. Action, Wikipedia, observation, this, and then it's going to have the final thoughts and telling you what's going to happen with that. Now, we perfectly used what we did with Elasticsearch and all the data used by Spark NLP to be transformed in our notebook with LangChain. What else can we do in test the quality of it? Obviously, you can make interactive applications, right? You could have different LLM models, and then you can go around and see what will happen if you start, asking different questions and then comparing those questions, look into the articles, even click on it and go to the original articles and see how it looks like, right? These kind of stuff are pretty easy to build, especially if you are dealing with, let's say, click something. If you're dealing with the Streamlit apps or Gradio apps, they're easy to be built. Like these are all coming from the exact same Elasticsearch, from the exact same data we used for, let's say, Spark NLP. All right, so This is our webinar. Thank you very much for your time. Please do not forget to go on GitHub, Spark NLP project, so it can be up to date with every releases we have. And if you have any question, please, on the GitHub, there's discussion. We have a Slack channel as well, and you can reach out to me directly. Thank you very much.